are seeking to understand data center workloads, optimizing data center hardware and software to improve performance and energy efficiency. We wish to identify optimization targets within these massive workloads. We sample stack traces detail how software consumes processor time, and then construct call graphs that detail how software composes and is organized hierarchically. Given these call graphs, we can reveal the structure of massive software systems and identify hotspots for performance optimization, efficiency optimization. In the pursuit of these objectives, we encounter three significant challenges. First, discovering optimization targets. We wish to look beyond fine-grained hotspots such as malloc or memcopy and discover coarse-grained computation for which we can build more significant accelerated systems and architectures. Part of this objective is discovering synonymous computation. Can we identify functions that have different names but are essentially performing the same types of computation, whether it be memory allocation, compression, decompression, or serialization, deserialization? The second key challenge is interpreting these massive call graphs. We wish to analyze the directed acyclic graph where vertices are functions and edges are caller-callee relationships. And we want to scale the analysis of the call graph to tens of thousands of functions and hundreds of thousands of relationships. We wish to scale this analysis yet retain interpretability so that a system architect can look at our call graph analysis and reason about computation at multiple scales. And finally, we need to account for time effectively, which can be difficult. We want to avoid double counting time for functions and its subroutines. Limelight Plus is an analysis pipeline for data center call graphs that addresses these significant challenges. It does so with three major algorithms. The first algorithm partitions a large call graph into coarser layers, allowing a system architect to reason about computation at multiple scales. The second algorithm clusters semantically similar functions, providing a much larger optimization target for integrated and coherent acceleration strategies. The third algorithm identifies hotspots for optimization, either in hardware or software. We have already demonstrated Limelight Plus in a number of case studies. First, we've looked at a testbed where we examine Facebook's open source software repositories for PyTorch Cafe 2, RocksDB, and HHVM. In a second study, we looked at Facebook's production data center with 300 million stack traces and 240,000 unique functions. In a third study for DARPA, we looked at software assurance graphs that describe how a large piece of software satisfies specifications and requirements, again, with the goal of providing human interpretable results.